In this lecture, I am going to solve a numerical problem based on electric potential energy. Question is, four charges are placed along the corners of a square of side A. Calculate the potential energy of the system. This is the question. Four charges are placed along the corners of a square of side A. Calculate the potential energy of the system. So for solving this, first draw the corresponding diagram. Let us draw the diagram. It is a square. So there is a square of side A. So side is A. And four charges are placed. So let us place four charges. This is Q1, this is Q2, this is Q3, and this is Q4. Four charges are placed. Now we want to find the potential energy for the given system. For doing this, let us proceed in the same way as we discussed for the triangle. So what we did in that case, we considered that initially all the charges are at infinity. Now you will bring all those charges from infinity to the sides of the square one by one. Okay, so let us solve this problem in the same way. So let us imagine that all the charges are initially at infinity. Q1, Q2, Q3, Q4, all are at infinity. So many charges are there. You can consider so many charges, out of which you will take four charges. Okay, these are at infinity. Infinity means far away. Somewhere you are having charges. From there you will take charges and you will place in the given region of space and you will make a square. Okay, so first you will take Q1 from infinity and you will place here. Since in the problem they are not mentioning external field, by default it is in the absence of external field, because they are not mentioning any external field. If there is any external field, they will mention. So here they are not mentioning anything in the problem, which means there is no external field. So you are moving Q1 in a free space. There is no external field. That means it is very easy to move Q1 because there won't be any repulsive force exerted by your region of space. Okay, so it is very easy to move Q1 from here to here. You don't need any work. So W1 is 0. Okay, now after doing this you will move Q2. Now when you are moving Q2, it is not an easy process. Why? As you can see here, even though external field is absent, you are having one charge here, Q1. This Q1 will repel your Q2. So if you try to move Q2 from here to here, your Q1 will not allow you to do this process. This Q1 will always repel your Q2. So when you are moving like this, Q1 will repel. so it is not easy to move from here to here. That means you need to do external work to overcome this repulsive force exerted by Q1. Okay, so you need to do work W2. What is the equation? W is Q into V, as we discussed in the previous problem. Here, what is Q? The charge which you are moving. Which charge you are moving? You are moving Q2. And what is V? Potential at the point where you are placing your charge. Let us consider that this is point A, this is point B. So you are placing the charge Q2 at a B. So V is the potential at a B, that is VB. Isn't it? Now you can find VB. What is VB? You can find it. VB is equal to 1 by 4 pi epsilon 0. It is a point charge. Who is producing VB? Potential at B is produced by charge Q1. Q1 is a point charge. So the point B is at a distance of A, which is already given in the problem. Hence, at B, Q1 is producing a potential. Q1 is a point charge. Potential at a point due to a point charge. You know the equation. 1 by 4 pi epsilon 0 charge. Which charge is producing that potential? Q1 divided by distance, that is A. So VB is 1 by 4 pi epsilon 0 Q1 by A. Work done in this process is Q2 into VB. VB is 1 by 4 pi epsilon 0 Q1 by A multiplied by Q2. That will give you 1 by 4 pi epsilon 0 Q1 Q2 by A. This is the amount of work done to bring second charge from infinity to B. Now, after doing this, you will move the third charge. Let us say this is the point C. You are moving the third charge Q3, which is again at a distance of A. Now at C, there will be potential at C due to two charges. Both Q1 and Q2 will exert potential at C. So in the case of work done, there will be two terms because two charges are exerting potential at C. Okay, so here again it is QV, which is the charge you are moving, Q3, and V. What is V here? V, you are finding the potential at C, and it is exerted by both the charges. So the charge which is at A will exert a potential VCA plus Q3 into charge at B, that is Q2, will also exert potential at C, VCB. This is the expression. So if you want, here you can write it as BA, which means potential at B is exerted by charge at A. Okay, this is the way we will represent. Now you can write VCA and VCB. What is VCA? VCA is equal to 1 by 4 pi epsilon 0. A is producing, the charge at A, that is Q1, is producing a potential at C, isn't it? So this is the distance between A and C. You can see it is a triangle. In that, if you apply Pythagoras theorem, you can find that distance. It is root of A square plus A square. You can find AC. AC square is equal to AB square plus BC square, or AC is equal to root of AB square plus BC square. What is AB square? That is A square plus A square that is root 2a square, or that is equal to root 2a. So this distance is root 2a. Now what is the potential at C due to q1, which is at A? So charge is q1 divided by distance. Distance is root 2a. This is the potential at C due to the charge at A, that is q1. Now what is VCB? 1 by 4 pi epsilon 0. At C, the charge at B is also producing potential. Which is the charge at B? That is q2 by distance is A. From B, q2 to q3 distance is A. So you got the potential terms. Hence, what is the work done? W3. W3 will be equal to 1 by 4 pi epsilon 0 q1 q3 by root 2a plus 1 by 4 pi epsilon 0 q2 q3 by a, isn't it? Now you are having 3 charges, but your intention is to make a square. So bring the fourth charge. Your fourth charge will be at D. You will place the fourth charge at D. Now you got a square. At D, there will be potential created by 3 charges. Q1, Q2 and Q3 will make potential at D, isn't it? So there will be 3 potential terms. In this process also you need to do work, because all the other 3 charges will repel Q4. So in order to bring Q4 from infinity to D, you need to do work. The amount of work done in this process is W4 is equal to, there will be potential due to all the 3 charges. So there will be 3 terms for the work done in this case for the fourth charge. Which charge you are bringing? It is Q4, and the potential point is D. There will be potential due to charge at A. Then there will be potential due to charge at B, and there will be potential due to charge at C. Okay, now you can find VDA. What is VDA? 1 by 4 pi epsilon 0. From D to A, distance is A. And which charge is creating potential at D from A? It is Q1. So expression is 1 by 4 pi epsilon 0 Q1 by A. Similarly, what is VDB? 1 by 4 pi epsilon 0. Which charge is at B? It is Q2. And what is the distance from Q2 to Q4? This is the distance from Q2 to Q4. This is the distance. It is again same as root 2a, isn't it? So the distance is root 2a, and the charge which is creating that potential is Q2, isn't it? Q2 by root 2a. Now what is VDC? It is 1 by 4 pi epsilon 0. VDC means potential at D due to the charge at C. Which is charge at C? It is Q3 divided by distance between Q3 and Q4. It is A, because the side of the square is A. Now what is the work done? W4. 1 by 4 pi epsilon 0. First term is Q1 and there is a Q4. So Q1 Q4 by A plus 1 by 4 pi epsilon 0 Q2 Q4 by root 2a plus 1 by 4 pi epsilon 0 Q3 Q4 by A. So this is the work done. Now you got the system of 4 charges. So how much work you did in this entire process, that is the total work done, and this total work done is converted as the potential energy of the system. So find the total work done, then it will be equal to potential energy of the system. So what is the total work done? W is equal to W1 plus W2 plus W3 plus W4. W1, as you know, it is 0. Okay, so 0 plus what is W2? W2 is 1 by 4 pi epsilon 0 Q1 Q2 by A. So W2 is 1 by 4 pi epsilon 0 Q1 Q2 by A plus what is W3? W3 is 1 by 4 pi epsilon 0 Q1 Q3 by root 2A plus 1 by 4 pi epsilon 0 Q1 Q3 by A. By 4 pi epsilon 0 Q2 Q3 by A plus W4. What is W4? It is given here. 1 by 4 pi epsilon 0 Q1 Q4 by A plus 1 by 4 pi epsilon 0 Q2 Q4 by root 2A plus 1 by 4 pi epsilon 0 Q3 Q4 by A. So this is the net amount of work done. That is total work done in creating such a system of 4 charges placed along the corners of a square of side A. This work done is converted as the potential energy. So potential energy is given by this. Now if you want, you can take 1 by 4 pi epsilon 0 common. So potential energy is given by 1 by 4 pi epsilon 0. You can take common. Now in the first term, what is remaining? Q1 Q2 by A plus what is remaining in the second term? Q1 Q3 by root 2A. Q1 Q3 by root 2A plus what is remaining in the third term? Q2 Q3 by A. Then in the fourth term, Q1 Q4 by A. Fifth term, Q2 Q4 by root 2A. Q2 Q4 by root 2A. Then Q3 Q4 by A. Q3 Q4 by A. Isn't it? So this is the amount of potential energy associated with your given system. In the same way, you can solve any other problem. Method is that bring charges one by one and find the corresponding work done in the process. Then add all the individual work dones. You will get the total work done. This total work done is equal to the potential energy of the system. And remember that in this way you can solve problems when there is no external field present. In the case when there is an external field, you need to consider that also, which we will discuss in the next lecture. Okay, so by default, if they are not mentioning any external field, you can consider that external field is absent.